We've talked about three forms of supervised learning regression. We've talked about least squares, we've talked about weighted least squares, sort of the same thing with a weighting, and total least squares, which is a pretty different parameterization because what we're optimizing for is a little bit different, that perpendicular or shortest distance versus that asymmetric vertical or horizontal distance. Let me review that a little bit, and we're going to talk about some practical issues associated with running least squares and weighted least squares and these types of optimization, particularly with large data sets. So let me remind you where we were. We start with a simple linear model. Y is equal to u1x plus u2. And here I've replaced m and b for u to be more generic for some unknown. We established a quadratic error function, xu minus y. By here we are back to doing the vertical distances. We've got this vector norm squared. X, of course, is the matrix with the x coordinates in the first column, 1's in the second column, y are my y coordinates. And we set up this quadratic error function. And what that error surface looked like, remember, was a paraboloid. We have two unknowns, slope and intercept. And before I drew it as a bowl, and here I'm drawing it as a contour now, where small errors are in yellow and bigger errors get closer to blue and purple. Each of the contours here is associated with equal values of the error for the two parameters u1 and u2, slope and intercept. So think, if you will, just as if you're walking around that ridge of a contour that is an equal elevation. And what are we trying to do? We're trying to find the u1 and u2 that is associated with that minimum, the bottom of the bowl where the error goes to a minimum. All right, so nothing wrong with this. You could do this all day long. Let me just remind you, however, what the formulation looked like. So what we did is we took that quadratic error function and we differentiated it because it is a paraboloid and we know that the derivative at the minimum is going to be equal to 0. The derivative was 2x transpose times xu minus y. We set that equal to 0. Get rid of the 2, solve for u by bringing over the x transpose y over to the other side. And then we have this little 2 by 2 matrix here we're going to invert, and we're home. Yeah. And you can do this all day long to fit parameters to a linear model, a line, a parabola, whatever your linear model is, I don't care. So what's wrong with this? Well, nothing is really wrong with this, but remember that this matrix here, it's only a 2 by 2 matrix, it's not that bad, but the matrix multiplication itself is going to depend on n, the number of data points. And of course, if you start to have more unknowns, not just 2, but 3, 4, et cetera, well, then that matrix is going to get bigger and bigger. And we should think about the computational cost here. Up until now, the computational cost has been nothing because n has been 20. But what happens when you have this really dense sampling of tens of thousands, hundreds of thousands, millions of points? Well, matrix multiplication and matrix inverse are O of n cubed. So that matrix multiplication right there, x transpose x, is going to scale with the cube of n. And that can start getting very costly as n gets bigger and bigger and bigger. Now, you can say, well, let me sample the data. I'm not going to use all of it. But that's not a very rewarding solution because you're essentially conceding that you're going to throw away some data. And so we should think about this computational cost when we are dealing with large systems. And dealing with this computational cost is the topic of what is going to come next. What we're going to do is we are going to do something called iterative least squares. It's least squares the same way as before, but we're going to say that we don't have the computational muscle or the memory to compute that solution explicitly because of the cost of doing matrix multiplication, O of n cubed. And now the question is, well, what can we do to deal with that computational complexity? And what I love about this section is not only is this a very practical way of doing the optimization, by the way, nothing's changing in terms of the linear model. Nothing is changing in terms of what I'm optimizing. It's only that third step that we're changing, which is how we're going to do the optimization. And what, again, I like about this is that this chapter that we're about to do now is critical, essential to neural nets, and deep learning, which will come later on, and which of course are a huge part of computer vision. So the machinery that we will learn now is not just useful in doing these types of least square solutions, but is also going to be useful later on in the semester and anytime you go to use neural networks.